start the recording. Now, thank you for Rahim for the nice introduction of the opponent and the grading committee, and thanks for everyone to come here for my defense session. I'm extremely excited to give you this presentation about my PhD thesis, which is titled Constrained Counterfactual Explanations for Temporal Data. My name is Zhendong, and my supervisors are Panos and Isak. So let's try to get started. So I want to begin my presentation with a story that I had this morning. So I decided to take a walk in the morning and try to enjoy this nice and cold weather in Sweden. And then I got a notification from my sports watch telling me that that I have low cardio fitness from my walking. Then I was wondering why did this happen, and is there anything wrong? Then I clicked into this application page and I tried to see my cardio fitness level during the previous 30 days. And then this application page shows me a diagram, also indicates that there were 10 days out of the 30 days that I had below average. Then I became a bit more worried. I kept scrolling down to find some article to see how could I understand this problem more. And I found this article about cardio fitness in general. And then they actually suggest me to increase my exercise level, like running or cycling, or even walking up a few hills during outdoor walk. And that can improve my cardio fitness level and lead to a better health situation. And from this story I was telling about, I would like to highlight two main components. The first one is temporal data, where in the middle of the screen you saw these 30 days of cardio fitness measurement from my previous months. And the second one is counterfactual. And the counterfactual in this case was an actionable suggestion to help me to improve my body situation from below average to more like a normal cardio fitness. And those two components, they serve as cornerstones for my PhD thesis, as you can see from the title. And I will introduce those two aspects before I formally introducing each paper. So first one, what is temporal data? Temporal data refers to the data type that exhibits temporal dependencies. Examples can be seen here, could be ECG recordings, sports activity measures, or sales data. And this is considered time series data. And the second group over there, which could be patient admission events, medication events, or log events from the website browsing. And those can be constructed as event sequences. So what we can do on top of those temporal data is to apply machine learning algorithms on top of them. And we can see that this is a simple illustration where you can see from the left, which is the input X. In this case, it's an ECG time series. And then it's fed into the predictive model, F. And then it goes to the prediction Y hat. And in the case of ECG time series, it could have two different prediction outcomes. The first one is classification. For example, could be classifying an ECG if it's abnormal or normal. And the second outcome is forecasting. So here it could be using the previous 30 seconds of ECG measurement, trying to predict the next 30 seconds. And there is a challenge. The challenge here is that the predictive model in the middle, which is usually considered as black box. And then that leads to a lack of transparency, and we as users, we couldn't really understand what has happened inside the black box model. And to build on top of that, there has been deep learning methods trying to propose recently. There are a few state-of-the-art methods, like for classification, there are inception time, CNNs, LSTMs. And for forecasting, there are N-beats, N-hits, and also autoformer-based model has been proposed. So those models, they can achieve competitive predictive performance. But there are two questions that can be arisen by the user, which are, the first one is, how does the model make decisions? And secondly, can the model be trusted? So based on those two questions here, we as the users are in the need of model explanations. And I try to introduce two sets of post hoc explanation methods here. So the first one is feature importance methods, including shape and line, and also saliency maps. So the first group of methods, what they try to do is to highlight which feature input is more important compared to the others. And the second group here is to help us understand the model reasoning. In this case, it's counterfactual explanations. And the example could be, say here, if the patient could reduce the daily carbs, then one would have a lower risk of heart disease. And another more casual example could be, for me, if I rehearsed this presentation 2 more times yesterday, then I would pass it more easily. And actually, I followed this counterfactual yesterday, so I'll try to do my best. Given those background of the counterfactual explanations, I would like to show you one practical example in the risk prediction of heart disease. So imagine that we have a patient here with a list of his information, and he's a 43 years old professor with his blood pressure there and daily carbs and exercise duration. And this professor seems to have some overeating problems, which he eats 400 grams of carbs every day. And then he goes to a doctor, which has a black box model behind, and it tries to predict this patient, in this case, have a high risk of heart disease. Now what counterfactual can do is to suggest this patient to reduce his daily carbs intake from 400 to 180. And that can lead the patient to a lower risk of the heart disease prediction. And the benefit of this counterfactual approach is that it can provide the user with actionable insights of what has happened inside the black box model, and then try to uncover of this lack of transparency. And a bit more background of how the counterfactual explanation have been generated. What we try to frame here is called high utility counterfactuals. And there are a set of requirements or desired properties that they are more desired to satisfy. And here I put a list of 5 as example. So the first one is, does the counterfactual achieve the desired outcome? And that, in that case, is linked with validity. So a counterfactual should flip the prediction outcome to be considered as valid in that case. Secondly, how close is the counterfactual close to the original instance? Closer is better. So that leads to proximity. We want the counterfactual to be approximating the original instance, and we do not want to change too much of the input instance. And third one is, fewer feature changes are more desired. So that leads to sparsity. We want the feature changes to be sparse and not to be very change every possible feature, for example. And the fourth one is to offer multiple explanations for the user. That leads to diversity, so that the user can choose among a few different counterfactual suggestions. And the fifth here is to keep the change minimal and focused, making the explanation more concise. And that leads to compactness. And this is more connected with temporal data. And here I also try to highlight 3 of them in this red box. So those 3 ones, validity, proximity, and compactness, those are the ones I will try to mention them more in my related publications in this thesis. So given those background information, this PhD thesis identified 2 main research gaps. The first one is that the previous research work has been focusing on mostly with image or tabular classification problems, and they have not been investigated too much into temporal prediction, which could be classification or forecasting. And secondly, there hasn't been too much research work investigating counterfactual constraints to enhance their utility in the real-world scenarios to kind of support the real-world usage. And with that, this thesis formulated 3 research aims. And I tried to put some color-coded box to the left with some summary text so they can be a bit easier to connect them later on. So the aim 1 is about temporal prediction, which we would like to develop counterfactual methods for forecasting and for classification. Aim 2 is about constraints, where we would like to introduce constraints into the counterfactual generation problems. And that can be divided into domain-specific and local temporal constraints. So aim 3 here is to validate the effectiveness of the developed counterfactual methods, especially in the healthcare domain. And the main research question from the PhD thesis is formulated as how can we generate high-utility counterfactual explanations for temporal data using machine learning? And that can be divided into 4 sub-research questions. And similarly, I try to put some color-coded cards there. So SRQ1 is how and to what extent can we generate high-utility counterfactuals for event sequence classification and time series classification. SRQ2 is extending the same as SRQ, but generalized for time series forecasting. And SRQ3 here is to how can we incorporate counterfactual constraints into the generation problem. SRQ4 is how can we validate the counterfactual methods in real-world applications, in this case in healthcare. And this is a list of related publications from the thesis. I will not read through all the text here, but just try to highlight each paper and their corresponding venues there. And also I will use one slide to explain the highlight of each paper later on. So paper 1 was published at AMI 2021 conference, and it was the best student paper award back then. Paper 2 was published at AI Medicine AIM Journal. Paper 3 was published at the DS Discovery Science Conference 2021. Paper 4 was published at Machine Learning MARC Journal. Paper 5 was published at ICDM Conference 2023. Paper 6 was published at CBMS Conference this year, 2024, right before the summer. So try to provide the overview before I talk into each paper. So those 3 research aims, they are divided and linked with those 4 sub-research questions. And each sub-research question is linked with different papers. So SRQ1 here is linked from paper 1 to paper 4. And SRQ2 here is linked between paper 5 and 6. So SRQ3 about constraints is linked between paper 2, 4, and 6. And SRQ4 applications is linked with paper 1, 2, and 6. And those 6 different publication papers, they are also grouped afterwards into 4 individual studies based on their predictive tasks. So here, paper 1 and 2 were grouped into study 1, 3 and 4 into 2, 5 and 6 into study 3. And I will talk into those papers by their grouped studies right now. So the first study is to provide counterfactuals for event sequence classification, and it includes paper 1 and paper 2. So here you can see the paper index. Paper 1 was published at the AMI 2021 conference, and it's linked to the right bottom of the sub-research questions. And that's the same layout for each paper, so hope you can connect a bit easier. Yep. Okay. There seems to be some issue with the Zoom connection, but we just continue as we are here. Yeah. So we were talking about the connections and trying to group those 6 different publications into 3 individual studies. So I'm going to talk about each study right now. So the first one was to provide counterfactuals for event sequence classification, as we already mentioned. And then the paper index and also the sub-research questions are demonstrated for each slide of the publications. So in paper 1, we proposed initial MedSec CF, and here is one example you can see, which is constructed from the patient admission records using all the medication events. And the upper one here, or you can see that it leads to, maybe I can highlight, yeah. So the upper one here leads to a high mortality risk of the prediction problem. And now with this counterfactual, is to try to suggest this orange box to remove some medication events and insert 2 more medication events. And that can lead to low mortality risk of the patient outcome. So this counterfactual was generated by adapting the DRG method from text style transfer. So here, D and R stands for delete and retrieve, where they pre-processed the input event sequences based on the relative frequency. And the generate component is to use LSTM encoder-decoder trying to generate the counterfactual X prime. And a quick summary of our empirical findings are highlighted there, which is MedSec CF outperformed the baseline in terms of BLU4 and LOF score. Those 2 are proximity metrics for proximity, while obtaining comparative validity. And in paper 2 was published at AI Medicine Journal, and it was extending the sub-research questions with SRQ3, which is to incorporate constraints into the mechanism. And in this augmented MedSec CF approach, where you can see there's a highlight of the model structure. I will also try to do the magic here to highlight them. So here you can see this original input sequence, which is a red one, which is a negative outcome. And after feed into this LSTM encoder-decoder structure, it gets to the positive outcome, which is to the right-hand side. And now, what we did additionally here is to incorporate this additional mechanism. The first one is to incorporating patient diagnosis codes from the history into the modeling approach. And secondly, we incorporate this existence information of medication events also extracted from the history of medical records. And this is trying to avoid, for example, drug and drug interactions in the modeling procedure. And our findings here are that by taking account into this additional information from the medical background, they can improve the baseline in terms of validity and LOF score, and also outperforming the baseline in terms of BLU4 score and edit distance. So now moving on to study 2, where we try to focus on providing counterfactuals for time series classification, and that includes paper 3 and paper 4. So paper 3 was published at DS Conference 2021. And here's the illustration of our proposed method, latent CF++. And I also try to highlight with a marker here. So this is an illustration of the the algorithm, how it works from the beginning to the end. You can see to the beginning of the algorithm, we have the input X, and then we fed into this black box classifier, and it gets to the prediction, which in this case is a red box and a negative outcome, and the desired outcome is a positive. And then we go into this gradient-based search approach using a loss function, and also using latent or representative models like CNN autoencoders and LSTM autoencoders. And after this gradient-based optimization, we try to update the sample to X star here, and X star is called the counterfactual candidate. And then we fed this candidate back into the black box classifier again to generate the prediction. And here, if it's a red box again with a negative outcome, then we will repeat those a few blocks over again and again. And after this iterative approach, until we reach to the right-hand side here, which is get to the positive outcome of the prediction, then we generate it as an outcome of the counterfactual. So from this approach, we found that latent CF++, it demonstrated high validity and margin difference compared to the state-of-the-art methods. And also, it obtained comparative proximity in this case for the counterfactuals. So for paper 4 was published at Mark Machine Learning Journal, and also extends the paper 3 with additional SRQ about constraints to the right. So in this proposed method last year, we tried to extend the previously mentioned latent CF++ with local constraints. And the highlight here is we incorporate this constraint vector C in the optimization problem. And by introducing this constraint vector, we essentially trying to tell the optimization objective, trying to focus on certain time steps and trying to encourage the change at certain time steps rather than change the whole time series as a counterfactual. And there are two different ways to obtain the constraint vector C. One is example-based, example-specific, based on line segment. And in this case, it's trying to generate an important segment for each time series individually. And the second approach is global constraints, where we propose this interval importance, which is similar to random forest, where we shuffle the intervals and find the important intervals for each time series region. And here I would like to highlight the results by showing two examples. So here you can see the example-specific constraint, where we have the abnormal ECG classification. And to the left, you can see this unconstrained version, where all the areas are highlighted in this red color. And the one in the right, you can see, which is example-specific, where the red bars are highlighted the region that this counterfactual should focusing on. And you can also see that the blue color line is the original instance, and the red color here is the counterfactual instance. So by changing this line from the blue to the red, it can lead to a normal prediction of ECG rather than abnormal. And another example I would like to show is the global setup, where we have the automated failure detection problem. So it's similarly to the example-specific approach, we try to highlight these red bars, and those are the regions we try to focus the change to encourage the counterfactual change to happen. The findings from the experiment here is that last year demonstrated competitive performance in terms of validity, proximity, and compactness. And those two instantiations demonstrated a trade-off in favoring different constraint regions, and also the trade-off in terms of the metrics measurement. So now it's the last study I will talk about, which is to provide counterfactuals for time series forecasting. And that includes paper 5 and paper 6. So we have been talking about the counterfactual setup in the classification tasks, where we have the negative outcome, like unhealthy patient to healthy patient, by posing the change in the red circled area. But how about forecasting? When we have the historical values of maybe 10 years of sales data, and then we try to predict the next 5 years for the sales data. How do we define the outcome? Because it's not as trivial as positive or negative. And our answer here is to define an upper and lower bound for the forecasted values for this forecasting horizon. And with that idea, we published paper 5 at ICDM conference 2023. And in our proposed method, forecast CF, here I'll try to highlight the result by showing an example of the sales forecasting. And you can see that from here, the blue line is the original sales data for the previous 14 days. And to the right, those blue dots are the 12 days of the forecasts that the original value fall within too. And to the up, you can see that's the constraint bound with these dashed curves. And now with the forecast CF method, it's trying to suggest counterfactual change to the input sequence time series by posing this change of this orange-like line. And that leads to the outcome of the cross points prediction that are fall within these constraint bounds. And by zooming in a little bit into the bounds, so there are a few different parameters that we try to define for this instantiation we call polynomial trend. And we try to define the center of the band, also the width of the band, and also the change percent from the beginning and until the end of the 12 days, how much we would like them to increase. And also we could also identify, define different polynomial orders, and it could be 2 or 3 or even more curly bounds that can be incorporated. So with this paper, we found that forecast CF obtained better validity and also data manifold, in this case with proximity and compactness compared to the baseline. Also, we observed the trade-off between validity and the other group of metrics when we did the ablation study. So when we increase the demand for validity, then somehow it leads to sacrification of proximity and compactness. And paper 6, the last one, extends the SRQs with constraints and applications. So in this proposed method COMET, where we try to generalize the forecast CF into a multivariate setup, into a multivariate forecasting problem, in this case focusing on glucose level prediction. And here I try to highlight there are 5 different variables, and the top one is glucose, and the last 2, the second 2 and 3 is basal and bolus insulin, and the last 2 are daily carbs and exercise level. So with the previous 2 hours of measurements, then this patient is predicted to have a hyperglycemia risk during the next half an hour, which is above 180 in the measurement. And now, too quick. Now with this counterfactual constraints we try to incorporate in this case, it's try to suggest its counterfactual change using the orange arrows. And with the suggestion of the basal insulin and exercise level, this patient now can lead towards the normal glycemia, which is below 180. So those cross points are the predictions. And those this counterfactual is generated by using 3 domain-specific constraints. The first one is to encourage change at a specific activity period, like meals or activities. When they happen, then we try to change. And also second one is to clip outer range values using the minimum and maximum value. And this, okay. And then the third one is closely resemble the historical inputs using the additional inputs. So our findings here is that COMET generated clinically relevant and also sparse suggestions with high compactness and proximity, also with a reasonable validity leading towards normal glycemia. So let me summarize the main points of the research aims and which ones we addressed and how they are connected with each papers as a conclusion. So aim 1, temporal prediction. Paper 1 and 2 proposed MedSec CF, trying to address event sequence classification problems. Paper 3 and 4 proposed Glacier and latent CF++, trying to provide counterfactuals for time series classification. Paper 5 and 6 proposed forecast CF and COMET for time series forecasting problems. And regarding the second aim, constraints, paper 2 and 6 proposed domain-specific constraints for 2 different prediction scenario. And paper 4 and 6 proposed local temporal constraints by focusing the change into specific regions of the time series input. About the aim 3, validation, paper 1 and 2 focused on the problem of mortality risk prediction in the ICU setup. Paper 6 focused on the problem of glucose level prediction for diabetes patients. And to mention a little bit about the future directions, I have 2 points I would like to highlight. The first one is that our proposed methods, they are regarded as more general counterfactual frameworks. That means they can be plugged in or unplugged with certain components in the middle. So that can be expanded by, for example, exploring more recently developed latent models like GANs or diffusion models into the modeling problem. And also it can be generalized with some other instantiation or desired outcome, in this case, trying to expand the work. And secondly, these domain-specific constraints, they can be further investigated and tailored to different applications, so to facilitate the real-world scenario. And my 2 cents here is that there would be 3 steps towards human involvement in the counterfactual research. So the first one is to involve the user into the assessment phase, which can be asking them to mark relevant or not, or some other kind of annotation things to do, to use as a feedback of the counterfactual generation. And the second step there would be conduct larger user studies with, for example, medical professionals to understand the needs and about the development and deployment of the counterfactual methods. The last one here would be create a human-in-the-loop system where the user can, in real time, choose maybe the desired property as an input and to get real-time feedback directly from the counterfactual system in real world. So as a final remark, I would like to leave you with 1 sentence here. It's not really linked with my PhD thesis or my research area or my research papers. It's from a book that I recently read, and it's called Social Psychology, so by David Mears. And David said, counterfactual thinking underlines our feelings of luck. So basically, he tried to like justify that during some situation, we can think, as humans, can think of negative outcomes to make us feeling lucky. And with that, I think probably it's a good idea that I started exercise tomorrow, and then trying to improve my cardio fitness level, and also try to maybe strengthen my feelings of luck. And this is a list of references I have. And thank you so much for your attention.
Thank you. Thank you. So we go for the next session. Michaela. 50 minutes presentation by the opponent.